Ok, online.
Vamos esperar. Let's wait a little bit so that it starts broadcasting. It's not yet.
It's open, broadcasting.
Okay. Thank you very much, Vinicius. Welcome everyone to this new webinar from Learning from the Extremes. We always have every week a new super nice webinar to you. We hope that you enjoy it. Thank you for being with us. So today we have with us David Souza. I have to say proudly that it's a member of Nucleus team. We have running the show Vinicius Oliveira, who is replacing Gustavo today. And David, I'm going to introduce David, who is the speaker for today. David is a physicist by training, and he has 2 master degrees, one in anthropology and another one in cognitive sciences. But he's not speaking of any of those topics today. He's going to be talking to us about electronics and programming with Tinkercad. So, David, I'll have to warn you that there is a lag between what you present here and what the audience will be seeing. There's some time, so don't expect a quick answer. I will be monitoring the chat on YouTube. So if you have questions to David, please keep them coming. And I know that you're going to have a super duper presentation that will have us all be willing to master Tinkercad in no time. So thank you very much.
Hello, everyone. Thank you for being here. So the topic of today, as Rosa said, is electronics and programming with Tinkercad. This is a super tool that you should learn how to use. I'm going to share my screen now. So I guess everyone can see now. Tinkercad is software online in the cloud from Autodesk. You can do 3D modeling with Tinkercad. You can do circuits building and simulation, and you can even code those circuits, or you can do programming, block programming of shapes and interactions between shapes. Today, it's going to be about electronics and programming. This is a super tool because it can be so engaging in the classroom. You could get your kids, your students, to pick up the computer and do so many kinds of simulations of circuits. It's really mind-blowing, and I'm going to present some of these examples. It can help you to build your own prototypes that then you can build physically if you have access to the components. And if you don't, well, you can test many things without breaking these components, burning up LEDs. So it's super useful, and it's super interdisciplinary as well. So the first step is really to sign up. If you want to do it now, you can do it. Otherwise, you can do it later. It's as simple as this. You click sign up, and then you can register as an educator. You can register with a personal account, or you can enter with a join code as a student. So we are going to go here, educators. And after reading the teacher agreement, which gives you a bunch of tools that you would not get having a student account, and you agree with the terms and conditions, and then you can sign up either with your email account, your Google account, Apple, Microsoft, or Facebook. I already have an account, so I'm going to straight go to that, sign in. And as soon as you sign in, you get this dashboard here. On your dashboard, you have on the left a list of collections that you can create for your designs. You can access your designs on the left as well, and tutorials. If you ever come across tutorials, they will be stored here and you can access them at any time. Also, you can create classes. This is super useful because your students don't need to create an account. So for instance, if you want to create a class, you create a new class, you enter the name of the class, LFE webinar, you select the grade, other, subject, general education, robotics, can be art, for instance, generate class. And then you enter your class and you start adding students. For instance, Maria, João, but notice that you have to give them a nickname as well that they will use to enter this class. And when you go back to your class, you see your students here. There is a share class link here that you can use to share with your students. And when they get into the class, they'll have to use this code here to join the class. There are a couple of instructions. There are two ways of doing this. I'm gonna copy this here to show you how to do it. Then access the class as a student. Tinkercad join class. That's me. So when students go to that link, they put the name, the join code, and they can enter the class. I can show you more examples later if it's easy for you. But now we go back to drawing circuits. So on the left, I have my collections. When I want to do a design, I click on create. And here I can choose between 3D design, circuits, or blocks. Today we are going to do circuits, so I'll click circuits. However, before we create a new circuit, I wanted to show you some examples of things that you could do. So I go to my collection webinar, and I choose, for instance, the interplanetary scale. Every time you select one of your examples, this panel will show up where you can choose to copy the link to share with other people or just simulate it. Or if you click Tinker this, you go directly to it and you can change it. I'm gonna explain you all of these tools on top and on the right after. First, I'm just gonna show you a couple of examples. So as you see, there are so many components on Tinkercad that you can use. Here, I'm using an Arduino Uno. I am connecting it to an LCD screen. I'm using a push button and a force sensor. For the sake of the example, and because we don't have weight sensors in Tinkercad circuits, I'm using a force sensor. This is just for the sake of the simulation. The Arduino is like the brain in the circuit. It's the tool, it's the component that connects all the other components and make themselves talk to each other. So to simulate this, I just click simulation. You're gonna see that the code that it's written here, which could be blocks as well, in case this is C, because it allows for more complexity. The code that is written here, it's the code that it's going to run inside the Arduino. So as you see, this is the kind of examples that you can make in your classroom because they are so interdisciplinary. In this case, it's about astronomy, although it uses electronic concepts. So you are actually learning both things at the same time. So when I click my force sensor and I change it, I can see the weight, my weight on planet Earth on the LCD screen. Don't bother about the units here on the force sensor. I'm using a force sensor just to replace a weight sensor, which there is not on Tinkercad. And then when I click the push button, I can see my weight on other planets, just because I have programmed the Arduino to use a factor that allows me to know my weight on other planets. And each time I click the button, I go to the next planet. This is a very simple example that I can later share with you, and it can try to implement physically in your classroom. We did this in our makerspace, and it is a success. So very interesting example that allows to put together astronomy and electronics. Go back to Earth. So I'm going to stop this example now. And I go back to my dashboard to show you other examples of things that you can do. Last week, you learned about the microbit. Here, you can use the microbit too, although you can connect with other components that Tinkercad has available for you. So here, I'm going to show you a very simple example of a Morse code machine. I have 2 microbits, and each one of them is connected to a pair of LEDs. Microbit offers 3 volts, so I have to put resistors, 1 for each LED, and they can communicate with each other through radio. I have connected the LEDs in a breadboard. We'll be talking about this later as well. And I have connected the microbit, each one of them, to the breadboard. So when I start the simulation and see that the code here is blocks, because I choose it to be blocks, it could be other kind of coding, but blocks is always a good way of learning how to code. When I press start the simulation, just see what happens when I click button A on microbit on the left. Did you see the light flashing? There is a little lag because it uses a lot of my computing resources, but you can still see some flashing on the LED. If I press button B on microbit on the right, I should see a flash on the left here. So each microbit is talking to another microbit. This is also a very interesting example that you could do with your students. And instead of having LEDs, I could have, for instance, a motor or a servo motor, and I could use 1 microbit as a remote controller and another microbit as the brain of the robot that I want to control. So let's go back again and start our drawings. So to start our drawings, we could create in our designs, we could create a circuit. And we get this blank area that we now have to start filling in with electronic components. On the top, you have some of the tools that you will need to use all the time. On the right, you have all your components. You can list them in a gallery like this, or you can list them with descriptions like this. You can show only basic components. We'll mainly be working with basic components, but you could also list all the available components. And there are so many things that you can choose. Even a potato battery and a lemon battery, which is really interesting examples for kids to use. So when we want to use something, we just grab that thing. I'm going to put calorie listing here because I liked it more. we just grab it and bring it to our area, and we can move this around. We can move everything that we put here, we can move it around. On the top, there are various things you could do when you have a component selected. For instance, if you select a LED, you can copy that and then paste somewhere else. Or it's the same thing as if you were working with files and folders. You can just click it and use your keyboard, Control-C, Control-V, to paste a new LED. You can delete it with the hotkey delete, or you can press delete on top. And you can always go back when you do something that you didn't want to do. You can leave comments, write something here, LFE amazing webinar. You can hide those comments, or you can show the comments again, and you can move the comments around as well. So what do we need now to make this LED flash? I could also use a light bulb. I will start with a simple example, a light bulb. Notice also that I can rotate these elements. I can either use this tool up here, or I can press R on my keyboard, the hotkey R, and the LED will rotate. Also, I can mirror it if I press M on the keyboard or I click here on top. You can see I can mirror. It's easy to see because there is the anode and the cathode, and they are different. One is longer and the other one is smaller. I can, to make this bulb light up, use a power source, of course, and there are many different power sources that you can use. You can use a potato, you can use a lemon, but you can also use a 9-volt battery, for instance. I can type battery here, and I get all these different types of batteries. 9-volt battery, AA battery, coin cell battery, and see the voltage is written here already. And every time I click one component, I can change its properties. So for instance, not all of them have properties to change. Well, all of them have names, but not all of them have properties, other properties that you can change. For instance, for this battery, I can choose the number of batteries inside. I can use 4, I can use 2 batteries. I can put a switch on, off, and I can, for instance, use AAA batteries instead of AA. So I'm gonna, for the sake of this example, I'm gonna rotate this. This example is going to be about understanding. This is something you can do with your students, the relation between tension and resistance and current. Let's see what happens if I connect this battery here to the bulb. The bulb is not bipolar, so I can connect like this. You can use the hotkeys or the colors here to change the color of your wires. Also, you can change the type of wire. I can use a hookup, or I can use an alligator, but I prefer the normal one because it just uses less space. And I like to use red, which is number 2, or I can change it here. Red for positive and black for negative. Let's see what happens if I start my simulation. Right, it works. Now I cannot change anything when I'm in simulation mode. I can just see the result of the simulation. Let's see what happens if I swap the wires like this. You can zoom in and zoom out to be sure that you do things right. And it still works. But what will happen if I use the LED? Let's connect this red wire to the LED here. And here, it doesn't work. Why? Because it's a diode. It's a light-emitting diode. Diodes also emit energy. They emit photons, but they don't emit photons in the visible range of light, and LEDs do. So let's just swap again these wires like this and see whether it's working or not. It doesn't work. Why? Because it burns out. It's too much energy for this LED. So in this case, we would have to use a resistor. So we're gonna look for a resistor here because it burns the excess amount of energy that we have, and we can put it in any direction in the circuit and in any parts of the circuit, because it just changes the electromagnetic equilibrium in the circuit. And we can change the amount of resistance in this circuit by clicking the resistor and changing this number here. But let's see what happens with 1K ohm. It works. Let's see if I click. This is a thing that you can change while you do it live. While you are doing a simulation, you can change this resistance here. And you see that the colors of the resistor are changing accordingly, and the intensity of light in the LED is changing as well. It's dimming because it's too much resistance for this LED. Now, to do this, it's much more practical to use a potentiometer. So this is an adjustable resistor. And this is already a little bit confusing here. Let's delete this light bulb. Also, let's mirror this LED so that the wires don't cross, and use here a potentiometer instead. You notice that when I click the wires, when I'm using the wire tool and I click on my working area, the wire is making some shape. I'm shaping the wire. If I click on the top of a wire, I can change it as well like this. This is very practical because it sometimes can get very confusing. So let's test this now with LED. All right. Too much resistance. Let's change the amount of resistance in our potentiometer. Maybe use 1K. Still too much. Not too much here. But then it starts to dim. All right, let's exchange this for a bulb. Because it's easier to see the changes. You see how the intensity of the light changes. And I always have a 9-volt battery. But here I'm gonna swap for something else. I'm gonna use a power supply, because then I can get a reading for the voltage and a reading for the amps as well. So you see how the potentiometer is decreasing the current, the amount of current in the circuit, because I'm increasing resistance. I could, for instance, as well use multimeters in the circuit. This is very useful because you can put them at different points in the circuit. For instance, I could use one multimeter for reading the voltage at our light bulb, and I could use another one to read the voltage in our potentiometer. And this will allow us to understand better this relation between tension, current, and resistance. And again, another one to measure the current in our circuit. All right, so let's see what happens now. So I'm going to measure current here. I'm going to measure volts here. There is a negative sign here, and it's positive here. Let's move this up. And as you increase the voltage here, you also increase the current intensity in the circuit, and therefore the light intensity. If I change my potentiometer level here, I can see that as I increase resistance, I'm also decreasing measured amps in the circuit, and I'm consuming more tension on the potentiometer and less here on my light bulb. So this is, let me just swap the wires. Okay, so this is an easier example here to understand this relationship between potential difference, resistance, and current. So let's go to another example now. Just gonna show you that you can use push buttons, for instance, to control the light bulb or even switches. So I'm gonna connect the push button here to my light bulb. Sorry, my Tinkercad is a little bit slow. Now I'm gonna go back and enter again through my dashboard. Sometimes it can consume many resources in your browser. So I'm gonna connect my push button like this to my light bulb and see how it works. So when I click the button, it lights up the bulb. If I hold Shift while I click the button, it stays lit. I could instead use a switch. Let's use a switch here. Connect the light bulb, the switch, and the power supply to the switch. And because this little thing here is connecting these two terminals, the light bulb is lit, but if I move it to the other side, it's not anymore. So this is a very, very useful thing to do. Now, shall we move on to another example? I'm gonna create a new design here. You can try doing these things at the same time as me. If you split your screen, you can watch the video at the same time that you try out some of these examples. We are going to use a breadboard now. This is very useful as well. So as my mouse moves on top of my breadboard, I can see what holes are connected to each other. Everything here in each vertical line is connected. So on line 27, all the 1, 2, 3, 4, 5 dots, holes are connected to each other. Everything on line 10 is connected to each other again. Everything on the plus line is connected to each other again. Everything here on the black negative line is connected to each other as well. This makes it very useful to use one power source connected to here and then all the other components on the rest of the breadboard. So in this exercise, we can make a strip of LEDs, for instance, that are connected in series, and another one that is connected in parallel. Another exercise to show how these two different ways of arranging circuits work. I can move a LED here. If I click this LED, I can change its color. I'll keep red for this one and then move another one here. Make it green. Another yellow. Change it for orange, blue, and white. Now to connect them in series, I have to connect the anode of one to the next cathode of the other. And because they are in different vertical lines, I can use any hole on one of the lines that is connecting the anode here to any hole on the vertical line where the cathode of the other LED is. I will use red because I like red and connect all of them to each other. Now I need a power source. I will use the power source that I used before, the power supply, because then I can control the voltage and I don't have necessarily to put resistors. And I'm going to connect here positive output to the positive line and the negative to the negative. And now I am able to connect these LEDs to the power source. So I can, for instance, use this hole here for negative and this hole here for positive. And let's see what happens. You see, I can control the voltage. And they are all lit at the same time. You see an exclamation point there. It means that you have an alert for the amount of current that you are giving to each LED, so you cannot go over a certain threshold. Now let's do the same, but in a parallel circuit. We can copy this actually. If you hold Shift, you can select all the LEDs, Control C, Control V, and then move it under to the bottom. And now, so notice here that I have one main branch. This is the one main branch here, the negative with the positive line. And then to this one main branch, there is another branch, which is this one here that connects all the LEDs in series. Now, again, I'm going to put another power supply to the bottom of the breadboard. Then bring this negative wire here. And I have a new branch, a new power branch. And now instead of making one branch for all the LEDs, I make a branch for each one of them. So I connect the anode, the positive, with the red wire, like this. Again, the negative, the same way as before. And repeat this for each LED. All right. Are you trying this out as well? So let's see what happens now. Right, I'm going to give more or less the same amount of current. You can also change it here. You can choose a voltage of 10, for instance, or 12 is a good number because they are well lit. And here, change it to 12 as well. But now notice that I cannot put 12 here on this because they are in parallel. So if I provide 12 volts to this main branch here, and they are in parallel, it means that each LED is gonna take 12 volts from the main branch. So I have to decrease it until it works. I can do it like this. All right. 2 volts is a good value. You see the differences. Now you can use a multimeter if you want to measure the voltage for one LED only. For a couple of LEDs, we can do that. Let's go grab a multimeter. Grab it here. And now let's connect positive wire here to one of these LEDs on the positive leg, the anode, and a negative wire here to the cathode. Let's see how much it gives. It gives 2 volts. So the voltage is distributing itself through this array of LEDs. If I, for instance, move this negative wire here, and instead of grabbing this LED's negative leg, I put it here, I get 4, the sum of these two. If I move it here, really good and simple exercises that you can do with your students. Let's try it again. So I'm taking the voltage of 1, 2, 3, 4, 5 LEDs, which is 10 in 12, because I'm not considering this one here. So what happens now if I remove one LED here and I remove one LED here? So what happened here? It doesn't work anymore because they are connected in series, but here they still work because they are independent from each other. This is a really good exercise to teach the differences between connecting in parallel and in series. So I hope this was useful to you. We can now move on to another exercise. Just before showing something we can do with microcontrollers, we go back to the dashboard here And now that you did some examples and you learned about the potential that this has, you can explore the gallery and you will realize that there is so many people sharing so many different projects from which you can learn from which your students can learn from, just by using the very simple components that Tinkercad makes available. For instance, you can use, as a startup, you can use the weather station that somebody else created. Let's go to circuits here. In this example, for instance, he's using a temperature sensor, a soil moisture sensor, an LCD, and he's probably using this LED strip here to show the level of one of the measurements. For instance, you could take this as an example, as a starting point from something that you want to do, but there are many different weather stations that people are doing and making available for others. Some are more complex than others. This, for instance, uses a buzzer to make sound. So probably when the temperature goes over a certain threshold, it makes a sound and it leads the LED. This one is using a motor and a servo. I don't know why. Probably it's making itself movable to escape high temperatures. I don't know. So there are so many things you can try. Or you could, for instance, search for an air quality station example. And here you see people are using gas sensors. This is a gas sensor. An LCD probably to tell you the amount of gas in the air. So many things to explore. Now, if we go back and we go to designs and create a new design for us, you will see that apart from all these basic components, category, this all category where you can find all components, and there are many things here. Different kinds of power supply, function generator, oscilloscope even. This is a really small microcontroller. You can use a microbit as well. Attetine, just compare the size of an Arduino with an Attetine, and this can already do so many things that the Arduino can, although it has only 8 pins. This processor here is of the family of this big processor here, AT Mega, although it gives many other possibilities, the Arduino. So let's go down and see there are different kinds of gates, logic gates that you can use. And you can, if you go to starters, start with a basic circuit that you can modify with an Arduino, for instance. If you go back, we can use more space. Just push, for instance, this one here, servo. And let's see what it does. I don't know what it does. We can look at its code, clicking code. So there is some complex code that someone created for this servo. Let's see what it does. If we click on start simulation, all right, starts rotating in different directions. You could use push buttons with this. You could use radio. Now I can move another example here. I can move one that uses an ultrasound sensor. Just fit here. Let's see what it does. If I click on the ultrasound sensor, it will probably just output something on the serial monitor. Yeah, exactly. So you can use a serial monitor here, like the same when you use the Arduino software or the microbit that have serial monitors as well to make your readings. Here on Tinkercad, you can use as well a serial monitor to monitor the changes. So as you see, as I move this little ball around my perception field, the perception field of the ultrasonic sensor, I can see changes in inches and centimeters. This is for Arduino 2. So I'm using two Arduinos at the moment here. If I click here, I can exchange between Arduino 1 and Arduino 2 and work at the same time with both. I can even add a microbit example. We move this microbit with moisture sensor, an alarm, maybe. You can use all of them at the same time and make them communicate with each other. Now, when I simulate this, which should be very resource hungry, you see how much time does it take for 3 seconds to pass? If I go to code again, and I can choose between the different circuits here that are programmed. Now, a very useful thing is to use more classical notation. If you want to share it with someone, you can click here on top, this middle button, and you will have these classical drawings for circuits. And imagine you have such a big circuit, you can also count your components, each type of component you have, because maybe you want to buy these things, like everything works, and now I want to order these things to build the physical prototype in school. I can use this and download this information as well. Now let's do something different. I'm gonna go back and create a new circuit. So in this example, I'm gonna use a breadboard because it just makes things easier. I'm gonna use the AT-Tiny because it just uses less space than the microbit. See all the AT-Tiny. Where are the microcontrollers? Okay, the AT-Tiny because it just doesn't use much space. And you see how it connects automatically to the holes in the breadboard. And this little thing here can use between 3 volts and 5 volts input. So I'm gonna use a coin cell because also it doesn't take much space. And I will program this thing as an automatic switch for 2 LEDs. How do I do this? First, I need my LEDs. Basic. Bring one LED here. Bring another LED here. Gonna change the color. And now connect positive wire here to the positive row. Negative terminal here to the negative row. It just makes it more easier for me. It's more intuitive to see how the current flows from top to the bottom when I'm building my circuit. And now when you pass your mouse over the little terminals, you will see what it is, what they are. This one is for power. So I can connect it to power by putting a wire in any of these holes here with this one because it's closer. And then raise ground. Let's look for the ground. It's here. We connect this wire here to the ground. Now we need to connect these LEDs to the AT-Tiny. So we connect the positive leg, makes it easier that I mirror them. positive leg here to one of these wires here. I'm gonna use another color now, orange, and see, I'm gonna use this color here for the second lead on another pin and connect the lead here. Now I have to connect both these cathodes to ground, although I will need the resistor because I'm providing 3 volts and I think it's too much. We can try and see whether it's too much or not. Let's program this without resistors, and if it doesn't work, we'll use resistors. Connect this leg here. I have to do this because there is no connection in the middle of the breadboard. If the AT-tiny was here, this pin would be connected to the ground, this pin power would be connected to this one, and if then I was providing power to the AT-tiny here, I would probably do some crazy stuff to the AT-tiny that I would not want. Maybe I would burn it, I don't know. So I have to separate it. I put it here for that reason. And now I have to program the AT-tiny, so I go to code. And there is some predefined code here that we don't need, but we'll use forever because this is something that we want to do forever to light up these LEDs. Just move this to the garbage. And now we'll look for set pin 0. Is this one 0? This one is 0, this one is 1. So let's just light them up both at the same time. Set pin 0 to high. Low means that no energy, no signal will reach the LED. Let's do the same for pin 1. So we set both to high, and now we test this. So not working for one of them. By connecting this to the wrong place, 1 is 0. Or am I not providing enough energy? Because they look like they are both connected, right? Let's try with another kind of battery. Let's mirror this. So of course I damaged the AT-tiny and I was not providing enough energy for the LEDs. Let's see if I put some resistors here, whether this works better for the LEDs and the AT-tiny. Change the resistance here. Almost. It will happen many times that things don't work straight and you have to tweak a little bit around to see, to find the mistakes that you are making. Not connecting the AT-tiny now. Now I am, but only one LED is working. Well, anyway, we have to move on because time is reaching the end. So we'll use this ATtiny and this LED only to... so it was not enough energy for both. Well, no worries. We can program this ATtiny now. Would block wait to make some time pass before we set pin to low again. Wait a second and then set pin 0 to low. All right, let's test this now. Okay, let's put another block right here. You see how it blinks. I could instead use a push button, but then it would not be automatic. I would have to push the button every time. I could use a switch, but the same would happen. This is why microcontrollers are so useful, because they can do things automatically if you want to control robots that react to different things like temperature, to the presence of gas in the atmosphere, whatever really. And here you can program this. I'm not sure whether you can use C as your coding for ATtiny, but it looks that this option is not available. Anyway, blocks is a really good way to learn how to program and a really good way to learn logic, because many times people start learning to code with very complex, very difficult languages, and many times they don't understand the logic behind things. And what's more important is to understand the logic. Is like Latin languages. The grammar is the same across the different languages, but the words that you use are different. And with programming languages is the same thing. You can use C, Java, JavaScript, or blocks, which is really simple, and that is a really good thing. And you have to use the exact same logic, otherwise things don't work. So really good thing to learn logic and computational thinking. So I hope you did like this session. This is just a starting point for you to start building your own prototypes of, who knows, interplanetary scales, robots, anything that you can imagine. And don't forget that you don't need to reinvent the wheel. There are so many things that others have done already that we can learn from. And you can learn from specifically this gallery here when you select circuits, because people are creating such amazing stuff. You can select any one of them and you will learn something new. So I hope this session was... And Vinicius, Rosa, I am done.
David, thank you
If
very
you'd say
much.
something.
I loved it. I have to say that I didn't know some of the things that you showed. I'm now really willing to learn more. So thank you super much for this very complete session. I'm sure that people watching this webinar will learn a lot. I mean, what an amazing tool for inquiry-based learning, for having the students build their own projects and test before burning everything at the lab. So they can train and do all the mistakes and understand why things worked one way or the other. So that was really brilliant. Thank you very, very much. I think it's you have shared with the audience a wonderful tool. So, and okay, this is now recorded, it's a legacy, so people that couldn't be with us today will then be able to see the webinar later. And I'll also take the opportunity already to announce to the participants that next week we have another webinar. It's about 3D modeling and printing. Sit with each other, get to know each other, who are the people behind the scene in learning from the extremes. We are also going to be supporting schools in writing Erasmus proposals for mobility actions and for partnerships. And very important as well, we are already announcing the final conference for learning from the extremes. Please go check the website, register, make sure that you don't miss this opportunity, that you are with us. And I think with this, I pass the word to Nikos. Nikos, hi, I haven't seen you before. Glad you are here with us. And so I think you have the honor to close the session today.
I was just about to say that thank you for the honor at least closing the session. I was able to join with 5 minutes lateness. David, thank you for this very interesting webinar. Thank you all for your participation. And as Rosa said, stay tuned. We have a series of very interesting webinars. And keep visiting our websites for any news about upcoming webinars and the conference. Thank you again.
Bye-bye,
Thank you.
everyone.
Bye.